Hello everyone, I'm Anushri R from ECE department. Today I'm going to make the videos on basic electronics, which is a subject included for the first and second semester engineering students irrespective of all the branches, which is going to have a subject code as 18 ELN 14 or 24. Before looking into the concepts or the modules, introducing the module, let me first brief you about the syllabus that is actually included in the basic electronics subject. It is going to consist of 5 modules. The first module consists of semiconductor diodes and its application. The second module consists of FET and SCR. The third module consists of operational amplifiers and its applications. Fourth module consists of BJT applications, feedback amplifiers and oscillators. The fifth module consists of digital electronics and fundamentals of it. The course outcomes of this subject are: it is going to describe the operation of diodes, BJT, FET and SCRs. It is also going to explain the construction and working of rectifiers, regulators, amplifiers and oscillators. This also explains the working principle or the operational amplifiers and its applications. And next is it is going to explain you the different numbering systems and their conversions and construct simple and combinational and sequential circuits. So these are the course outcomes that this is the course outcome at the end of the subject you can expect. Now, let us begin with the first module, which is nothing but our semiconductor diodes and its applications. So before going into the semiconductor diodes and its applications, let us first have the concept of what is a PN junction and what actually it is made up of. What is going to happen when it is not when it is in the unbiased condition, and what is going to happen whenever it is in the biased condition. So what is a PN junction? We already know P is a p-type semiconductor and n-type semiconductors. My p-type semiconductors are going to have a majority charge carrier of holes, and my n-type semiconductor is going to have a majority charge carriers as electrons. When we sandwich the p and n junctions together, now the holes that are present in the p region have a tendency to move towards the n region, and the electrons in the n region have a tendency to move towards the p region. As a result, it constitutes a junction which we call it as PN junction or a depletion region, where the barrier potential is going to get created, and we call that potential as barrier potential. Now, whatever the holes that have crossed the p region is no more called as positive, or the holes, it is called as positive ions, and the electrons which have crossed the n region and entered into the depletion region are no more called as electrons, it is called as negative ions. Once, this is before the unbiased condition. When we start biasing the PN junction, we call it as whenever we sandwich the P and N junction together, we call it as a diode, which is given by the logical, which is represented by the logical symbol. It is as shown here, with a cathode plate and a anode, which is nothing but a arrow, which will give you the conventional current flow direction. Now, let us study whenever we bias the PN junction diode. We have two types. We can bias the PN junction in two types. One is forward bias characteristic and the other one is reverse bias characteristic. For the forward bias characteristic, we are going to connect the N region to the negative and the P region to the positive. Now, as a result, the like poles have a tendency to repel each other. As a result, there is the movement, the holes move away from the junction and the electrons also move away from the junction. As a result, the depletion region is going to narrow down. The width of the depletion region is going to narrow down. Now, as a result, there is a movement of electrons, free electrons. Now, which will constitute a current which we call it as a forward current or a diode current, which is represented by ID or IF, diode current or a forward current. Now, once this is forward biased and there is a flow of current, I can say my diode is now in a closed switch. The diode is now going to act as a closed switch, right? So my diode is now going to act as a closed switch. So that is what is shown here. Now when I plot a characteristic curve of current versus voltage, there is a voltage which we call it as threshold voltage. Till it reaches the threshold voltage, the diode reaches the threshold voltage, there will be no flow of forward current, which we call it as IF, and the voltage we call it as VT, which is nothing but our threshold voltage. The threshold voltage for the silicon is 0.7 and for the germanium is 0.3. For the germanium is 0.3. Now this current we call it as forward current. So this is about the forward characteristic, and whatever the current that is constituted here in the forward bias condition is due to the majority charge carriers that is present in the junction or the diode, right? Now let us go for the reverse bias characteristic. In the reverse bias characteristic, we can see the P region is connected to negative and the N region is connected to positive. Now as a result, unlike poles attract each other. That is, whatever the holes that is present in the P region will move towards the negative terminal of the battery, and whatever the electrons that is present in the N region will move towards the positive and they get neutralized. Now as a result, the depletion region's width starts widening. The depletion region width starts widening, and there will be the majority, there is a point where all the majority charge carriers are going to get neutralized and it is only left with the minority charge carriers. Now as and when I increase my reverse voltage, my diode will not have any current. Suddenly when it reaches the voltage which we call it as breakdown voltage, VBR, at that point or at that voltage, I can expect there is a sudden rise in the current, and that current we call it as reverse saturation current. Now, which are the charge carriers that is contributing a reverse saturation current? That is due to the minority charge carriers. The minority charge carriers are the one which is responsible for the reverse saturation current. So this is about the reverse bias characteristic. Now, after studying the reverse bias characteristic, now let us go for the relationship between the voltage and the current through the PN junction. I can represent the forward current ID or IF as equal to IS, which is nothing but my reverse saturation current, K, which is nothing but my Boltzmann constant, that is 11,600 by eta, where eta is equal to 1 and 1 for germanium and 2 for silicon. VD is nothing but the voltage across the junction, and Tk is nothing but my temperature in degree Kelvin. That is, no matter whatever might be my temperature in Celsius is getting converted into degree Kelvin. So this is what is a relationship for the diode current. Now, after knowing the relationship between the voltage current through the PN junction. Now let us go for the breakdown region. We already know there are two, what is breakdown? There, wherever, as and when we increase the breakdown, as and when we increase the voltage, reverse voltage, there is a region where actually the device is going to get damaged at a certain point. Now that point we call it as a breakdown voltage. Now there are two kinds of voltage, breakdowns. One is Zener breakdown and the other one is avalanche breakdown. The Zener breakdown is caused by the strong electric field in the depletion region, whereas the avalanche breakdown occurs due to the wider depletion region. Now this is what is the total VI characteristic curve of a PN junction diode, which is shown both for the forward bias characteristic as well as the reverse bias characteristic. Now after studying the VI characteristic of the diode, let us study about the equivalent circuit of a diode. Equivalent circuit is nothing but it is a proper combination of circuit elements like voltage sources, current sources, resistances, etc. There are three equivalent circuit of a diode. One is ideal model, other one is approximate model, and the other one is a piecewise linear model. In the ideal model, we represent the diode by using simple when we make the that is by considering the ideal condition when current I is equal to 0 and voltage V is equal to 0. Current that is we represent the diode as a simple switch. When we go for the approximate model, the name itself suggests it is an approximation model with the diode represented along with a threshold voltage Vt, where the dynamic resistance Rd is ignored. Similarly, when we go for the piecewise linear model, here along with the approximation model Vt, we are going to represent the dynamic resistance Rd. So that is what is shown here. Along with diode, we are going to represent the dynamic resistance as well as the voltage Vt. So in this video, we studied about the PN junction diode, its characteristics, its equivalent circuit diode, the type of breakdowns that is going to happen. Hope this video makes you beneficial for your studies. Thank you. Hello everyone. In the previous video, we studied about the center tap full wave rectifier, where the center tap full wave rectifier used a center tap transformer in which the load resistance was connected across the center of the secondary winding of the transformer, and we used two diodes. During the positive half cycle of it, only diode D1 was conducting and diode D2 was not conducting. Similarly, when we went for the negative half cycle, the diode D1 was not conducting, that is, it was in the reverse bias, and my diode D2 was in the forward bias condition. As a result, I could see the conversion of AC voltage happening both in the positive as well as the negative cycle. Now, after this, we also studied the derivation or the expressions for the average or DC voltage and current, that is given by IDC or I average is equal to 2Im by pi, and VDC or V average is given by 2Vm by pi. Similarly, we also derived an expression for the IRMS value and the VRMS value. For the IRMS value, we got Im by root 2, and for the VRMS value, we got Vm by root 2. Similarly, we also derived an expression for its efficiency, wherein which it proved the efficiency of the full wave rectifier is more compared to the efficiency of the half wave rectifier. In the full wave rectifier, whether it could be a center tap rectifier or the bridge rectifier, which we are going to study in this video, the efficiency is going to be the same. That is, we got the efficiency of the full wave center tap rectifier as 81.81%, and the ripple factor is equal to 0.408, right? So this is what we studied in the previous video. Coming to the bridge wave rectifier, we had some of the drawbacks in the center tap full wave rectifier. The disadvantages of center tap full wave rectifier are here, since we are using two diodes, since we are using two diodes, whatever, we must have the diodes, that is, in the previous half wave rectifier we used only a single diode, but for the center tap rectifier we used two diodes. These diodes must have high peak inverse voltage, and the another disadvantage is each diode we use will have only one half cycle of the transformer's secondary voltage, the DC output, is comparatively small. So this was a drawback for the center tap rectifier, which led into the foundation or into the study of bridge wave rectifiers. So we can see here the bridge wave rectifier is going to incorporate, as usual, with a transformer. The primary winding of the transformer is given with the supply voltage, and the secondary winding of the transformer, when the primary winding of the voltage, when the primary voltage is applied to the when the voltage is applied to the primary winding of the transformer, the secondary voltage the voltage across the secondary winding is going to be through your primary winding. So when we look into the graph, the waveforms during the positive half cycle of the input, that is represented as Vs, the input is represented as Vs. During the positive half cycle of the input, that is from 0 to pi, the diodes, that is, we use actually in the bridge wave rectifier 4 diodes. The connection of the diodes are done in such a way that the polarities are very much important when we connect the bridge wave rectifier. So once we use a 4 diode, and when we give the positive half cycle as its input, now the diodes which are opposite, that is D1 and D3, that is, we can look through the polarities across. the polarities across the point, let me name this point as A or the node as A and node this as B. Now, once the positive cycle is applied here, I can say the polarities across this, the secondary winding is going to be positive and negative, and it is as shown here. Now, once this is going to become positive, point A is positive now, can I not say my diode D1 is now in the forward bias condition? Look into the diode D2. Is it in the forward bias? No, this is because it is a reverse bias. Now look into D3. My cathode is connected to the negative terminal, so I can say my D3 is forward biased. So my diode D1 and D3 are forward biased, whereas my diode D2 and D4 are reverse biased. So I can say during the positive half cycle, my diode D1 and D3 is on and my diode D4 and D2 are off. Similarly, when we go for the negative half cycle, of the input, I can say, that is, when I give a negative half cycle as my input, I can say the polarities across the secondary winding of the transformer is negative, positive. Now what is going to happen? My diode D1 is now in the reverse bias condition according to the polarities, and my diode D2 is now in the forward bias condition. Similarly, what is going to happen with respect to D3? Because this is a positive terminal, I can say my diode D3 is in the reverse bias condition and my diode D4 is in the forward biased condition. So during the negative half cycle of the input, I can see my diodes D2 and D4 are forward biased, and it is going to act as a closed path. That is, if I represent this during the positive half cycle, I can say my diode D4 is a open circuit, my diode D1 is a closed circuit, so continuous. Similarly, my diode D2 is a open circuit and my diode D3 is a closed circuit. So this is my D1, D2 and D3. This is how my circuit is going to be during the positive half cycle, and during the negative half cycle vice versa. This is going to become closed switch and these two are open switch. So the inference that we are going to get from the bridge wave rectifier working principle is, during the positive half cycle, the two diodes are going to conduct, and during the negative half cycle, the opposite two diodes are going to conduct, right? So as a result, I can expect both at the positive as well as the negative inputs, waveforms, I can expect the conversion of AC into DC waveforms, right? Now, coming to the um, uh, average voltage and average currents, that is, whether it could be average current or DC current, we call one and the same. So when we come for the IDC or I average, I can say the very same expression holds good for the bridge wave rectifiers, that is, IDC is equal to 2Im by pi, right? So the very same expression holds good for your bridge wave rectifier also. Similarly, when I go for the VDC, this is also equal to 2Vm by pi. Similarly, when we go for the IRMS value, my IRMS value is also equal to Im by root 2 as in the center tap rectifier, and my VRMS value is also equal to Vm by root 2. But the only thing that we are going to vary in the efficiency as well as the ripple factor is, we are going to replace the RF resistor with, wherever we find the RF resistor, we are going to replace it with 2RF. So no matter whatever could be my the same step holds good, but the only thing the way there is a variation is we are going to substitute wherever we find RF into 2RF, right? So this is what, so when we come for the efficiency, the very same efficiency, this is also going to provide you 81%. And similarly, when we come for the ripple factor, that is gamma is equal to 0.40. So there is no difference when we use a bridge wave rectifier or a center tap rectifier. Because of the drawback of the center tap rectifier, we are into the bridge wave rectifier. That is, the drawback was the diodes used must have the high peak inverse voltage, right? So as a result, we are into the bridge wave rectifier. Now, we know everything is same, but even the bridge wave rectifier is going to find or is going to have some drawback. Now, what is the drawback? I can say in my bridge wave rectifier, I can find 4 diodes, right? So there is a presence of 4 diodes, wherein which, since there is a presence of 4 diodes, I can say there is a more number of power dissipation happening, right? Power dissipation is more in case of bridge wave rectifiers. Okay. Now, in order to conclude the rectifiers part, let us look into this chart where this gives you a relation for various kinds of rectifiers with its parameters that we have derived. Okay. Now, when we come for the IRMS, that is RMS load current, for the half wave rectifier, let me name this as half wave rectifier HW, and this as a center tap full wave rectifier CFW, and this as a bridge rectifier, so BR. So when we look into this, my IRMS or the IRMS load current is equal to 1 by, Im by 2 for the half wave rectifier, and for the center tap full wave rectifier it is Im by root 2, and for the bridge wave rectifier it is Im by root 2. And when we come for the VRMS, that is RMS load voltage, we have Vm by 2, Vm by root 2 as my center tap rectifier, full wave rectifier, and for the bridge rectifier it is Vm by root 2. Similarly, when we go for the power conversion efficiency, which is given by eta, that is efficiency, it is given by, for the half wave rectifier, it is only 0.406. In order to show you the difference where you have to substitute 2RF, it is written in this form, or else you would have directly written it as 0.406. And when we come for the center tap full wave rectifier, I can say the efficiency eta is equal to 0.812%, and for the bridge wave rectifier, you can see the difference here. The substitution of 2RF is very well shown for this expression. So this is what you have to do whenever you are deriving the expression for bridge wave rectifiers, right? So substitution of 2RF wherever you find the RF values, right? So the efficiency is also same when you compare the center tap full wave rectifier with the bridge wave rectifier. Similarly, we have the ripple factor given by gamma, where gamma is equal to 1.21 for your half wave rectifier, and for the center tap full wave rectifier it is 0.483, and for the bridge wave rectifier it is 0.483. Similarly, the ripple or the output frequency would be equal to F for your half wave rectifier, but for your full wave rectifiers it is 2F. And similarly, the peak inverse voltage, that is PIV, peak inverse voltage, is equal to Vm for your half wave rectifier, and for the full wave rectifiers it is 2Vm. Similarly, we have studied the voltage regulation, which is given by RF by RL into 100% is for the half wave rectifier, and for the full wave rectifier it is RF by RL into 100%, that is for center tap rectifier, and for the bridge wave rectifier it is 2 RF by RL into 100%. So wherever we find the RF, we are substituting 2RF by RL into 100%. So hope this chart gives you an idea of the parameters with respect to half wave rectifier and the center tap full wave rectifier and the bridge wave rectifiers, which conveys you the various forms which conveys you the various parameters occurring across your half wave as well as the two full wave rectifiers that we have studied. So they should be in order to proceed with the problems, this chart is very much important, and knowing these formulas are very much important to proceed with the problems, guys. So I hope this video gives you an immense knowledge on the rectifiers, and hope this would be a beneficiary video for you. Thank you.